Hey, welcome. It's another Foster film. We're going to talk about volumes of revolution today. Just one example, and we'll start easy. The next film will be example 2. It becomes a little intermediate, and then a third disc method video where things become a little tougher. So, what do you need to know? Well, you already have a nice background with integration, and you'll see exactly what's going to transpire here as we work the disk method to figure out the volume of a particular shape that's created by taking a flat plane surface and revolving it quickly round and round a particular axis or line. So let us take a look. On your worksheet you have this same scenario. You don't need to write this down, but we've got 3 lines, 3 curves, and we need to plot those 3 and get a picture. We're going to take the graph of these 3 regions, which you will find will bound a region, and we're going to rotate that region around the x-axis as you see here. So this is an xy coordinate grid with the graph f of x equals root x drawn. You're familiar with that graph. The next curve is x equals 4. This is a vertical line passing through the x-axis at 4. Important to realize the intersection of root x and the line x equals 4 when I substitute a 4 in for x in f of x. I get that intersection point of 4, 2. The last curve that's going to be drawn here will trap the region. Y equals 0 is just a horizontal line that will coincide with the x-axis. So you see that region trapped now, and it's this, we're going to rotate this region around the x-axis. And just to emphasize the region further, we've colored it in. So some students can picture this without difficulty. Some students really have a difficult time. But if you can picture this dotted region rotating around the x-axis, it rotates around, comes out toward you, then beneath where it is, then away from you. It goes slow at first and picks up speed, rotating around the x-axis until finally it's really spinning quickly around that x-axis. And it's almost like pottery or something. And you can see in your mind's eye this 3-dimensional region that is created. So our next scenario is drawing the bottom of this region as if it were rotated around the x-axis. And then we've drawn a disk in there. And so that's just a circle that's drawn. It's got a center that coincides with the x-axis, and it goes up to the purple curve and down to the white curve. That's a circle. What you need next to a picture are a bunch of circles. Let's bookshelf them from left to right. A bunch of circles. I know they start small if you're building from left to right. Then they get larger and larger, and you continue to bookshelf these circles all the way until you get to that boundary of x equals 4. And what we're going to do is add up the area of all of those circles. Add up an infinite number of circles. You're hearing some parallel terminology here to what you've already been exposed to. An infinite number of circles, each having a very thin thickness of, in this case, dx. Infinitesimally small difference in x. So this allows for us to theoretically bookshelf every single circle from 0 to 4. And we're going to sum up. We're going to sum up all those circles. And when I say sum up, you realize, oh, you're going to integrate, huh? Yeah, we're going to integrate all those circles from 0 to 4. I know how to find the area of a circle, by the way. It's just pi r squared. I'm going to sum up all those circles from 0 to 4 and figure out what I get for an integral answer. So this is R with your drawn circle. And now you need to picture bookshelving these disks from x equals 0 to x equals 4. I know the volume then is going to be taking the sum integral from 0 to 4 of all those circles and adding them up. Well, I realize further that a of x, this is some area formula in terms of x. I know the area formula for a circle is just pi r squared. So we've replaced a of x with an area formula, in this case a circle, pi r squared. So we're going to integrate from 0 to 4 pi r squared dx. Now this radius is going to change per circle. You see that the radius is very small at first and then it gets larger and larger. How do I figure out that radius length? I'm going to go top curve minus bottom curve. The purple curve is the top curve, denoted by root x. The bottom curve is 0. So for each circle, the radius can be found by going root x minus 0, or simply root x. Back to our scenario here. We have a volume then. We are summing up all the circles from 0 to 4. We know we're utilizing the area formula within the integrand, pi r squared, for each circle. And we factor out the pi because it is a constant. And the radius equals root x. This again is a result of taking the top curve minus the bottom curve to figure out the radius of each circle. It's root x minus 0, or simply root x. So in lieu of that r in our integrand, we're going to put in root x. So our integral looks like this. I factor out the pi. We're going to integrate from 0 to 4 root x squared dx. Yes, you realize that root x squared is going to be a pretty simple scenario for us, and we are definitely walking before running here. So simplify the integrand. Root x squared is just x. So we have pi times the integral from 0 to 4 of x dx. Alright, I know how to integrate x. This is the power rule in reverse. Add 1 to the exponent, divide by the new exponent. The pi is still factored out. I have x squared over 2, and I'm going to evaluate that from 0 to 4. You may attempt at this time to get home solo. If you do FTC 1, you're putting a 4 in for x. 4 squared is 16, divided by 2 is 8. Minus a 0 in for x, kicking out a 0. So really, we're just pi times quantity 8 minus 0, which gives us 8 pi units cubed. So there's an example of the disk method, the first example of an easy nature. Let's move next to one that's a bit more difficult. Stay tuned.